we are going to continue the remaining part of instruction level pipelining, and the other important topic is known as data hazards. Before studying to data hazards, we have already studied the instruction pipelining, non-pipeline execution, the calculation of various parameters like speed up, throughput, efficiency, clock cycle, frequency, etc. So now we are going to study the data hazards. Let's continue about that. A major effect of pipelining is to change the relative timing of instructions by overlapping their execution. This introduces the data and control hazards. Data hazards occur when the pipeline changes the order of read-write accesses to the operands so that the order differs from the order seen by sequentially executing the instructions on the unpipelined machine. So this is the condition while the data hazards will occur. It simply means while the order of read-write access will get changed to the operands and it will differ from the order seen by sequentially executing the instruction, the data hazard condition will occur. As we can see from the example, consider the pipeline execution of these instructions. A table has been given, and from the table we can see that all the instruction after the add use the result of the add instruction in R1. The add instruction writes the value of R1 in the WB stage, which is shown as black, and the sub introduction instruction reads the value during ID stage ID sub. This problem is called a data hazard. Unless precautions are taken to prevent it, the sub instruction will read the wrong value and try to use it. The OR instruction can be made to operate without incurring the hazard by a simple implementation technique. The technique is to perform the register file reads in the second half of the cycle and writes in the first half. Because both write back for add and ID or for are performed in one cycle 5, the write to register file by add will perform in the first half of the cycle, and the read of the registers by the OR will perform in the second half of the cycle. The XOR instruction operates properly because its register read occurs in the cycle 6 after the register write by add. The next page discusses forwarding a technique to eliminate the stalls for the hazards involving the sub and add instructions. We'll also classify the data hazards and consider the cases when stalls cannot be eliminated. We'll see that compiler can do to schedule the pipeline to avoid stalls. Now, the other topic is dynamic scheduling. It is the term where the hardware rearranges the instruction execution to reduce the stalls, and the dynamic scheduling offers several advantages like it enables handling some cases when the dependencies are unknown at compile time because they may involve a memory reference. It simplifies the compiler and it allows the code that was compiled with one pipeline in mind to run efficiently on a different pipeline. These advantages are gained at a cost of a significant increase in the hardware complexity. The dynamic scheduling, a major limitation of the pipelining techniques is that they use in order instruction. If an instruction is stalled in the pipeline, then load later, the instructions can proceed. Thus, it means that if there is a dependency between two closely spaced instructions in the pipeline, it will still stall. For example, we have an example from the table in which three instructions are used: divide, addition, and subtraction, which have three values. Divide has F0, F2, F4, addition has F10, F0, F8, and subtraction has F12, F8, and F14. The subdivision instruction cannot execute because the dependency of add on divide causes the pipeline to stall, yet subtraction is not data dependent on anything in the pipeline. So this is a performance limitation that can be eliminated by not requiring the instructions to execute in the order. To allow the subsection to begin executing, we must separate the instruction issue process into the two parts. The first part is checking the structural hazards. When waiting for the absence of a data hazard, we can still check for structural hazards when we issue the instruction. Thus, we still use in order to the instruction issue. So if we want the instruction to begin the execution as soon as the data operands are available, thus the pipeline will do out of order execution, which implies the out of order completion. In the introducing to the out of order execution, we have essentially split the ID pipe stage into the two stages. The issue is to decode instructions and check for structural hazards. The read operands are meaning that wait until no data hazards, then read the operands. So the basic idea is what a reservation station fetches and buffers an operand as soon as it is available. The eliminating and the need to get the operand from a register. In addition, the pending instruction designate the reservation station that will provide their input. So finally, when the successive writes to a register appear, only the last one is actually that is used to update the register. As the instructions are issued, the register specifies for the pending operands are renamed to the names of the reservation station in a process called as register renaming, in which the names of register are rearranged or changed. So this combination of issue logic and reservation stations provides the renaming and eliminates the war hazards. So this additional capability is the major conceptual difference between the scoreboarding and Tomasulo's algorithm. Since there can be more reservation stations than the real registers, the technique can eliminate the hazards that could not be eliminated by a compiler. So this was about the data hazards and dynamic scheduling